Hello students, now having seen the basic laws of conduction and convection in the form of the Fourier's law of conduction and also the Newton's law of cooling respectively, Fourier's law for the conduction and Newton's law of cooling for the convection. Now I am going to give the law behind the radiation mode of heat transfer, that is the third mode of heat transfer in the form of the Stephen-Boltzmann law. Earlier I have defined the Fourier law of conduction from where we got the K. So whenever there is a conduction mode of heat transfer, K speaks about the conduction. Whenever there is a convection heat transfer, that which is a mode of heat transfer between a solid body and the surrounding flowing fluid or a moving fluid, which we call it as a convection mode of heat transfer, the H will represent the convection mode of heat transfer. I told you also the difference between K and H. K is the thermophysical property of the medium, where H is not a property of the medium, but H value depends upon the four thermophysical properties of the fluid: rho, mu, Cp, K. Okay. Now having seen those two basic laws, now let me give the basic law behind the radiation heat transfer, which is called as the Stephen-Boltzmann law. Stephen-Boltzmann law. Two different people, Stephen and two different people names. I am going to state the law like this. The law states that the radiation energy emitted from the surface of a black body per unit time and per unit area, is directly proportional to the fourth power of the absolute temperature of black body, is directly proportional to the fourth power of the absolute temperature of black body. The law states that the radiation energy emitted from the surface of a black body, in fact, this black body plays a very significant role. The black body plays a very significant role in the radiation heat transfer. The black body concept is the central concept in the radiation heat transfer. What do you understand by the word called black body? Black body is the body which absorbs all the thermal radiation incident or falling upon that. Whatever the thermal radiation incident upon a black body, nothing will be reflected, nothing will be transmitted, all of that will be completely absorbed by the black body. If it is a non-black body, what will happen? Some energy may get reflected, some energy may get transmitted, but in case of the black body, everything, whatever the energy that falls, everything in the black body swallows or absorbs. But very interesting note here is the word black is a misnomer. A thermally black body may not appear black in color to the human eye. You will come to see the real explanation behind that statement when I deal with the radiation chapter separately. Okay. But what I want to highlight here is that black body is only a thermal blackness. A thermally black body which is absorbing all the thermal radiation falling upon that may not appear black in color to the human eye. When you see that thermally black body, it may not appear black in color as such. The best example is ice. I will highlight about that concept, black body concept, later when I do with the radiation chapter. So this Stephen-Boltzmann law is stating about how much energy will be emitted from the black body per unit time and per unit area. Mathematically, It can be given as EB. EB is also called as the total emissive power of the black body. The total hemispherical emissive power of the black body, that is the radiation energy emitted from the black body per unit time and per unit area, is directly proportional to the fourth power of the absolute temperature, T in Kelvin only. The proportionality constant is sigma. The energy emitted per unit time per unit area, it will be watt per meter square. This sigma is called Stefan-Boltzmann constant, given by this value 5.67 into 10 power minus 8 watt per meter square Kelvin to the power of 4. Try to remember this value, because this value will be very often, not often, I can say almost every problem of radiation heat transfer, this particular value of this sigma will be used. Better you remember this, 5.67 into 10 power minus 8 watt per meter square Kelvin to the power of 4. So this is the units for the emissive power given as watt per meter square. T should be in Kelvin only. That means if the absolute temperature gets doubled, the radiation energy emitted from the surface of the black body will increase by 16 times. If the absolute temperature gets tripled, the radiation energy emitted will increase by 81 times. So look at that. The influence of the absolute temperature over the radiation energy emitted from the surface of any body. In fact, this particular T power 4 law, they also famously call it as the T power 4 law, is valid even for the non-black body also. Even for the non-black body, this situation will be valid. That means even for a non-black body, later we are going to see in radiation chapter that even for a non-black body, if the absolute temperature gets doubled, the radiation energy emitted from the surface of the body will increase by 16 times. So the temperature, absolute temperature, has a strong influence upon the how much energy will be radiated or emitted from the surface of a body. Radiation is a surface phenomenon. It's now the three modes of heat transfer we have understood. Conduction is an internal phenomenon inside a solid body. Convection is a boundary phenomenon between a body and the surrounding flowing fluid. If the fluid has got velocity, forced convection. If the fluid has no velocity but still there is a motion prevailing for the fluid, it is called as a free convection or a natural convection. So the convection is a boundary phenomenon. In fact, radiation is a surface phenomenon. If the two bodies are exchanging heat by radiation, that would happen between the surfaces of those two bodies. This radiation heat transfer will be happening between the surfaces of the two bodies. Radiation, I can say, it is a surface phenomenon in case of the solid bodies. Right. Now, we have seen the three fundamental laws, Fourier law, Newton's law and Stefan-Boltzmann law. Now, having understood the three governing laws behind the heat transfer, now I am going to start the conduction. Now, let us, having understood the three basic modes of heat transfer, now let me start the conduction chapter, and now separately we will analyze convection later, and then we will analyze the radiation, and then we will see the applications of the heat transfer in the form of the heat exchangers. Okay. So now first let me start about the conduction chapter, which is a big chapter, slightly bigger chapter. It will occupy around 35% or 40% of the 35 to 40% of the syllabus of heat transfer is in the conduction. Those are subtopics are many. As compared to the convection, radiation and heat exchangers, conduction is slightly a bigger chapter. Now let me start the conduction chapter. Let us analyze each case individually regarding this conduction mode of heat transfer. First case, conduction heat transfer through a slab. Conduction heat transfer through a slab. Now we have considered a slab of thickness B I have seen a slab of thickness B. The material has got a thermal conductivity K. The left hand side of the slab is having a temperature of T1. Right side surface of the slab has got a temperature T2. Q is the conduction rate of heat transfer happening through the slab. Okay. This is the slab having a thickness B. Left hand side of the slab is at a temperature T1 and right hand side of the slab is at a temperature T2. K is the thermal conductivity of the material of the slab. K watt per meter Kelvin. Now let us calculate what is the rate of heat transfer occurring through the slab by integrating that Fourier's law of conduction. Okay. So behind any mode of any conduction problem, what is the governing law? Fourier law. So before integrating that Fourier law, we have to make some assumptions, because in any heat transfer analysis of any problem, the assumptions are very much important. Let me make these assumptions. Number one, the most common assumption which we make in every heat transfer problem is steady state heat transfer. What do you mean by steady state? The temperature at any particular location will not be a function of time. At any location. At any given location, temperature is not a function of time. The best example for the steady state heat transfer is our human body. Our human body is at a temperature of 37 degrees Celsius, a normal human body. Morning, evening, afternoon, any time if you observe, the temperature of the human body, its temperature you will record it as a 98.4 Fahrenheit, which is equal to the 37 degrees Celsius. Okay, so that assumption you are making the steady state assumption for this slab. Generally, remember that whenever there is a steady state heat transfer conditions are prevailing, please remember that there is heat transfer happening, but the situations we are proposing as a steady state. That means there must be a source of heat, there must be a sink. That means what is the source here? There is some hot flue gases maybe supplying the heat this side, and this is the sink which is taking up the heat from this side. Okay. Unless and otherwise the source and sink are there, the steady state conditions inside the body cannot be maintained. I repeat once again, to presume or to satisfy that steady state heat transfer conditions, there must be a source of heat, there must be a sink. Source is supplying the heat, sink is taking up the heat, right? Number two, one-dimensional heat conduction. That is, temperature is a function of x only. At x is equal to 0, T is equal to T1, and at x is equal to B, T is equal to T2, T1 is greater than T2. Okay, that is why heat is conducting in this direction. The direction of the heat flow is the direction in which the temperature is decreasing. Okay. Third assumption is no heat generation in the slab. No heat is not being generated in the slab, and K is constant. Thermal conductivity of the material is constant. Later we are going to see the case of conduction where the conductivity becomes a function of temperature. I told you already, thermal conductivity is a thermophysical property of the material. It may be a function of temperature in some cases, but most of the cases of the heat transfer problems, we assume that K is a constant. Sometimes very few cases are there where K may be a function of temperature. We will see that case later. So with these three assumptions, we will integrate the Fourier's law of conduction. Fourier's law of conduction. The rate of heat transfer along the x direction is minus Ka dt by dx. I separate the variables because temperature is a function of x. Separate the two variables, temperature and x, T and x. Q into dx is equal to minus Ka into dt. Okay, now if we integrate it, x is equal to 0 to b. When you put the limits of integration, the advantage is that if you put the limits of integration like this, it becomes a definite integral. You would not have to write the constant of integration, right? You don't have to write the constant of integration. So because that becomes a definite integral. See, to satisfy this steady state heat transfer situation, the Q should not be a function of x. This Q should not be a function of x to satisfy that steady state heat transfer conditions. How do you understand that? That this way we can understand that. I am going to make you understand why this Q is not a function of x to satisfy this steady state conduction heat transfer. Supposing if we just take a small differential element of the slab of thickness dx, small differential elemental of thickness dx, this qx should be equal to the qx plus dx. This qx should be equal to the qx plus dx. Then only the steady state conditions can be maintained. Supposing if you take a small differential element of the elemental thickness of the slab dx, if there are 100 watts are entering into the slab, suppose that even 1 second there are 100 joules of heat is entering. In the same second, 100 joules of the heat must vacate from that right side of the element of the slab. In 1 second, if there are 100 joules of heat is entering, in the same second, 100 joules must vacate from the right side of the element of the slab. This is. Supposing if it is 100 is entering, there is only 90 joules are leaving, the remaining 10 joules will tend to accumulate inside that element, which will increase the temperature of the element from time to time, because law of conservation of energy must always hold. Energy can neither be created nor destroyed. Supposing if this is 100 and if this is 90, right side is only 90 is leaving, the remaining 10 joules may accumulate inside that element, resulting in the temperature of the element may increase with time. But we are from other side, we are telling that the temperature of the element must not change with time. See, that steady state means that. Steady state means whatever the temperature you see at any particular location, after 5 minutes, after 10 minutes, after 1 hour also, you should see the same temperature. That is called steady state. So to satisfy that steady state conditions, this qx and qx plus dx must have to be equal. I repeat once again, to satisfy that steady state, if you assume that there are 100 joules are entering here in 1 second, 100 joules are entering in 1 second, in the same second, 100 joules must be vacating from the right side of that element. These two must be equal. That I would like to write here. To satisfy steady state heat transfer conditions, qx should be equal to the qx plus dx. That is, q should not be a function of x. For that matter, the value of the Q here, what supposing from the left hand side of this slab, if you propose 100 joules are entering in 1 second, from the right hand side of this slab in the same second 100 joules must vacate. Whatever the heat that is entering here, the same heat transfer must prevail from the right side also. Assume that there is no heat generation. I have already mentioned this. So, to satisfy the steady state with if there is no heat generation, this Q and the right side heat transfer Q from the right hand side of the slab both must be equal, that is Q should not be a function of x. When Q should not be a function of x, you can take it outside the integral. We have assumed that K is a constant and the area of the slab would remain constant. Supposing if you just take this as the slab, if this is the direction of the heat transfer, in case of the slabs, the area of the conduction is the area perpendicular to the direction of heat transfer. That should not be changing in the direction of the heat flow. Remember that in any slab case, conduction, the area of conduction would remain constant in the direction of the flow. You can see here, this is the area of conduction. That area of conduction is not a function of x. So, when A is not a function of x, A is not a function of temperature also. So, K is constant, A is constant, you can take it outside. Therefore, Q is anyhow not a function of x, you can take it outside. The resulting integration will yield Q into, look at this, Q into B. After integration, Q into B, K into A, that is because area of conduction heat transfer will not change in the direction of the heat flow in case of any slab. Q Ka into T1 minus T2 implies Q is equal to, what is that Q? Rate of heat transfer through the slab. Q is equal to rate of conduction heat transfer through slab Ka Ka T1 minus T2 by B. Okay. You may write the note that in case of conduction heat transfer through slab, in any conduction heat transfer through slab, area of conduction heat transfer does not change in the direction of heat flow. Okay, so this is the area of formula for the rate of conduction heat transfer through the slab. But in case of the slabs, most of the occasions, majority of the occasions, we always calculate the rate of heat transfer per unit area, because area of the slab may not be given. In majority of the conduction problems, we always calculate the area of the conduction heat transfer, we may take it as a 1, and we will always calculate the rate of heat transfer, conduction heat transfer per unit area. In case if the dimensions of the slabs are given, we will consider, but keep in mind that the area of conduction is always the area perpendicular to the direction of the heat flow. That is rate of heat transfer per unit area of the slab, which is also famously known as heat flux. In this subject, this word flux keeps coming very often. Flux means per unit area. Q by A is K into T1 minus T2 by B. watt per meter square. Flux means, remember that, flux means per unit area. Rate of heat transfer per unit area is called as heat flux. B is the thickness of the slab and K is the conductivity of the material of the slab. It is the formula for heat flux for one-dimensional conduction heat transfer through a slab. Now, in this context, I would like to introduce the very important concept in conduction chapter called as electrical analogy of heat transfer. Electrical analogy of heat transfer. From that analogy, I am going to define thermal resistance concept. I am going to introduce thermal resistance concept, because this word, thermal resistance word, you will always be using it many problems of conduction. Particularly you will see in the many gate problems also it is given, and I am going to solve all the gate problems given in the heat transfer entire subject. In the due course of time, in the due course of the coverage of this subject, you are going to see that each and every problem of questions given in gate in the last 20 years I am going to solve all that in every chapter. Okay. So, we are going to see that the importance of the thermal resistance now actually, which I am going to introduce now is electrical analogy of heat transfer. Analogy means similarity. Concept of thermal resistance. Concept of thermal resistance. Analogy means, in English, analogy means similarity. In this analogy, we are going to compare the flow of the heat current. Now, if this is a thermal means the terms pertaining to the heat energy, that is called thermal. And the flow of the electric current, I will make it analogous to the flow of the heat current, that is the rate of heat transfer. That is the rate of heat transfer. In watts? So, Q is analogous to the flow of electric current. In this electrical analogy, we compare that the flow of electric current is analogous to the flow of the heat transfer or the flow of the heat current. Why there is a flow of the electric current in any electric circuit? Because of the EMF, because of the voltage difference. Okay. So, the reason behind the flow of the electric current is delta V or EMF, electromotive force, which is analogous to the why there is a rate of heat flow, why there is a heat transfer is happening, because of the temperature difference. Just like the EMF or the voltage difference is the reason behind the flow of the electric current, in the similar manner the temperature difference is the reason behind the flow of the heat current. Now, we have the electric resistance defined in ohms, and correspondingly we have the thermal resistance, right. Now, I will draw the thermal circuit and electric circuit. From the circuits, we can easily make out this comparison. Now, if we just look at the electric circuit, in the electric circuit, this is the delta V voltage difference or the EMF, flowing current is I, we have the electric resistance measured in ohms. Correspondingly, if you draw the thermal circuit, we have the temperature difference as the driving potential, we have the rate of heat transfer Q, and we have the thermal resistance. Okay. Now, if we just look at this, particular electric circuit, I am going to apply the Ohm's law, very famous law behind any flow of electric current. Ohm's law states that from Ohm's law, electric resistance is given by voltage difference divided by current. So many ohms. Okay. In the same fashion, we could write it here. Here, the thermal resistance is given by, in the similar manner, temperature difference divided by Q. This Q symbol which I am using, this is the Q symbol, is meant for the rate of heat transfer. So, what are the units for the thermal resistance? Temperature difference we measure in Kelvin or Celsius, because temperature difference can be, its value is same whether it is mentioned in Celsius or Kelvin, divided by watt. Kelvin per watt is the thermal resistance. This is the electric circuit, that is the thermal circuit. So, this is the general definition of the thermal resistance, temperature difference divided by the Q, rate of heat transfer, right. Now, having defined the thermal resistance, if you just look at that previous formula which I have derived, here look at this previous formula. This is the thermal potential, temperature difference, this is the heat current, right. So, the rest will be the thermal resistance based upon this formula. Earlier we had defined, therefore, for a slab where the rate of heat transfer is given by Ka delta T by B, rate of heat transfer, implies, for slab Q implies conduction thermal resistance. The first formula I am giving the conduction thermal resistance. Like this you will see totally four thermal resistances you see. The first formula I am giving. Totally in conduction chapter we will come across four different thermal resistances I will be putting up. Among them, this is the first one I am putting, conduction thermal resistance for slab only. Conduction thermal resistance for the slab is given by delta T by Q. From this we can write, what is that value you get? B upon Ka. So many Kelvin per watt. This is the formula for the conduction thermal resistance offered by any slab of thickness B. The B is the thickness of the slab, K is the thermal conductivity of the material of the slab, and A is the area of the conduction. If you just look at this formula, more the thickness of the slab, greater the thermal resistance. When the thermal resistance is more, the heat current will be lesser. Is it not? If you make the slab thicker, resistance also will be more. As such, the rate of heat current through the rate of heat flow, conduction heat flow through the slab will be lesser. If you also see, if the conductivity of the material of the slab is lesser, if this is lesser, or I can say, if the thermal conductivity of the material of the slab is lesser, this thermal resistance will be more. When this is more, this is lesser. When this is lesser, this will be more, because they are inversely proportional, right? So, when the K, like in case of the insulating material, supposing in case of the insulating material K is lesser, thermal resistance is more. When the thermal resistance is more, heat transfer rate is lesser. Supposing if you are wearing a very thick coat, like a thick sweater, have made up of some pure wool material. Wool has got very low thermal conductivity, pure wool. If you are wearing a sweater of thick sweater, you can think of like that, made up of some woolen material, which is a very good insulator of heat. Definitely you will feel more warmth. Warmth means hotness. You can feel more warmth in the peak winter. If you are wearing a sweater having a thickness, much thicker coat, made up of a very good insulating material like a pure wool. Pure wool has got a very low value of the K. okay, because it is made from the animal fur, that will be having the very low value of the K. If you have observed that all those animals particularly which will move in the very low temperature regions, in the very low temperature regions, if you observe the animals, nature has given them some protection. All of them will be having a thick hair on their bodies, because that thick hair of which will act as a coat, which will act as a thermal insulating coat against the extremely low temperatures, because there will be some animals moving around the extremely low temperatures, minus 30, minus 40, minus 20 degrees Celsius. And how do those animals survive? Because nature has given them that their bodies are having a thick coat of hair whose thermal conductivity is very low. So that hair itself will be acting as a insulating and protecting their bodies from the extremely low temperatures. Okay, so this is the formula, remember this, the first type of the resistance. Later we will see 3 more. I am going to write that higher the thickness of the slab and lesser its thermal conductivity, more the thermal resistance and lesser will be heat current. Heat current means, and lesser will be heat transfer rate. Heat transfer rate means heat current only. Okay. Higher the thickness means more the B and lesser the value of the conductivity. Now this particular thermal resistance concept which I had introduced, now I am going to put up in the second case, which is also an important case in the gate point of view, called as a conduction heat transfer through a composite slab. Case 2. Conduction heat transfer, composite slab means a slab comprising of more than one material. Composite means a slab made up of more than one material, maybe 2 or a 3, maybe attached like in a series connection or a parallel, whatever it is. Composite slab means you will see more than one material. Here the 2 different slabs of having 2 different thicknesses and 2 different thermal conductivity, because they are made up of different materials. K is a material property. Once the material changes, K value also will change. So both the slabs are glued together with there is no gap between in that junction. So they are perfectly in contact, and this will form the composite slab. Okay. Though the left hand side of this composite slab may be having the leftmost surface is at T1 degrees Celsius. This may be having the T2 degrees Celsius, and this may be the junction. This may be the junction. The temperature may be Ti. The temperature may be Ti. Okay. Interface Ti is the junction or interface temperature. Okay. 2 slabs are glued together. 2 slabs are glued together, and the junction temperature is Ti, leftmost surface is T1, right side surface temperature is T2. T1 is greater than T2, that is why heat is conducting in this direction. Now we are interested in calculating the rate of heat transfer through that composite slab. A is the area of the slab. As I mentioned already, the area of conduction heat transfer will not change in the direction of the heat flow in case of the slab geometry. For slab geometry, the area of conduction heat transfer do not change in the direction of the heat flow. Assumptions are very important in this subject. One dimensional means temperature is changing only along the x direction like this. One dimensional, steady state. Steady state means what? Temperature is not a function of time at any particular location. I already said, to satisfy this steady state assumption, there must be a source and there must be a sink. To satisfy any steady state heat transfer, there must be a source of heat. That source could be even some electric power, or maybe hot combustion gases, or maybe some steam condensing. Supposing if this is the source, this source of heat may be some electrical element I can assume, or rather steam may be condensing, liberating its latent heat of condensation, or rather there may be hot combustion gases. By combustion, some hot flue gases are generating the heat. Any combustion is an exothermal phenomenon generating heat. Some combustion of the fuel is happening generating the heat. So that source of heat could be anything, maybe electrical or chemical or like anything I say. And there is a sink. Sink is always there in the form of the atmosphere, ready to pick up the heat. Say for example, my body is at steady state. What is the source in my body? Metabolism, metabolic activity. What is the sink? Atmosphere. My body is at steady state. Now at this moment, I am losing heat by convection to the surrounding air. But my body is at steady state. Why it is at steady state? Because there is a source inside. What is the source inside my body? It is a metabolic rate or metabolism which is generating the heat, biochemical reactions. What is the sink there? Atmospheric air. So because of the metabolism, heat is being generated. Because of the convection happening to the atmosphere, that is atmosphere is a sink. So my body is at steady state. Remember that to have any steady state heat transfer conditions to be satisfied, there must be some source of heat, there must be sink. Assume one-dimensional steady state conduction heat transfer. Now, this is the direction of the heat flow. This is the direction of the heat flow. So, okay. Now, I would like to calculate the rate of heat transfer by drawing the thermal circuit. The thermal circuit drawn will be containing two resistances T1, T2, Ti. First resistance will be B1 by K1A. Second resistance will be B2 by K2A. Q is the rate of heat transfer. Ti is the junction temperature or interface temperature. Ti is junction temperature or interface temperature. Perfect contact. There is no thermal contact resistance. I am in drawing this thermal circuit, there is no thermal contact resistance. What is these yellow colors lines representing? They are indicating the temperature profiles in the slab 1 and slab 2. Look at this. These are how the temperature is decreasing from left to right. That is indicated by these temperature profiles. These yellow color lines are the temperature profiles in the first slab and the second slab. Noticing that there is no thermal contact resistance at this junction. Okay, there is no any temperature drop there. Sometimes there may be some thermal contact resistance. If there is no perfect contact between the two slabs, maybe some little temperature drop may be there at that junction, but we always neglect that thermal contact resistance. Right, so this is the thermal circuit for that situation. Therefore, the rate of heat transfer through composite slab T1 minus T2 divided by, they are in series circuit. Why they are in series circuit? First of all, we have to notice that why they are in series circuit, because unless the heat current flows through the slab, that heat current cannot enter the second part of the slab. Unless the heat current flows through this first slab, it cannot enter the second slab. T1 minus T2 by, but as I mentioned already, most of the slab cases, we always calculate the heat transfer rate per unit area. I am not writing A1, A2 because I already said in case of the slabs, area of heat transfer will not change in the direction of the heat flow. Therefore, heat flux, most of the slab cases we always calculate. In the gate examination also, very often they always give the flux. But sometimes, few problems you may be having the dimensions of the slab is given. In case if they are given, we should consider that area perpendicular to the direction of heat flow. In case if the area dimensions of the slab are given, if this is the direction of the heat flow, we have to consider this area. Therefore, heat flux or heat transfer rate per unit area is equal to Q by A is equal to T1 minus T2 by B1 by K1 plus B2 by K2. So many watt per meter square. Okay, this is the formula for the heat flux through the composite slab. One important note that I would like to make out here, very important note I would like to make out here is that, very important note, that was the gate question asked also earlier. In case if the slopes are given like this, if these slopes are given, can you judge, can you tell by looking at that figure, can you tell whether conductivity of the K1 is more or conductivity K2 is more? That question was asked in one of the gate. In case if the temperature profiles are given like this, is the K1 more or K2 is more? I would like to judge. Yes, you can judge it easily. From the figure I can easily say K1 is greater than K2. This K1 is greater than K2, just provided these temperature profiles are given. Why like that? That answer is given from the Fourier's law itself. Q is equal to minus Ka dt by dx. Okay. Q is same throughout because it is a series circuit. Q is same throughout. Q is same throughout. Area of conduction is also same throughout because in case of the slabs, area of conduction heat transfer will not change in the direction of the heat flow. Q is same throughout. Area of conduction is also same throughout. K1 is greater than K2 since dt by dx in 1 is lesser than dt by dx in 2. dt by dx in 1, look at the slope. This dt by dx in 1 is greater than the dt by dx in 2. Okay. This slope is lesser, this slope is more. When the slope here is lesser, K must be more. Look at this, Q is same throughout. When dt by dx is lesser, K value must be greater. Therefore, K1 is greater than K2 since from the figure we can judge that dt by dx in 1 is lesser. This is lesser slope, this is more slope. Okay. When slope is more, K is lesser. K2 is lesser, K1 is more. That means I can say if the conductivity of the material is lesser, the steeper the temperature gradients through that particular material of the body. That is what I want to like to tell. Okay. So, very important case. Supposing in case if that most of the gate questions, they will ask you to calculate Ti. Very easy. Once you get the Q, this that same current is passing. Supposing if you just like that, if you are interested in calculating the Ti, that Q will be equal to, because we already calculated the Q here, Q will be equal to the T1 minus Ti, I is the junction temperature, divided by just only consider that particular resistance, because we have already calculated the rate of heat transfer. I know the T1, I know the B1, I know the K1, you can calculate Ti. If area is not mentioned in case of these slabs, we can always take it as 1. If area not mentioned in any slab problem, take it as 1. That means we will be doing the business per unit area, heat transfer rate per unit area. So from this we can calculate the junction temperature, or rather we can consider this one also, Ti minus T2, this potential difference divided by this resistance is equal to the current. We can consider that this particular potential difference also. Just writing the new Ohm's law. Potential difference divided by this resistance is equal to the current. Current we have already calculated. Q is the current, heat current. Rate of heat transfer is called as the heat current. So from that equation we will be able to calculate the Ti. This is a very important case. On this case many times the problems were given in the gate. Now having seen the one important type of the resistance against the heat flow in the form of the B by Ka. B by Ka is the conduction resistance offered by a slab, conduction resistance offered by a slab. Now I will introduce the second resistance called as the convection thermal resistance from the Newton's law of cooling. Suppose that there is a plate, hot plate, over which some fluid is flowing. Fluid, that may be air, that may be water. Fluid means anything, any moving gas, any moving fluid. Okay, even sometimes vapor also. Even the rate of heat transfer between the solid and the vapor also we treat it as a convection only. Convection is the mode of heat transfer that is occurring between a solid body and the surrounding fluid, just like the heat transfer between our body and the surrounding atmospheric air. The temperature of the plate is Tw, the free stream temperature is T infinity, the mode of heat transfer happening is convection. Okay. From Newton's law of cooling, the rate of heat transfer by convection is equal to HA delta T, right? So many watts. That is this is only famously known as Newton's law of cooling. But already we have mentioned the concept of the thermal resistance. The delta T is the driving potential temperature difference. What is the delta T here in this situation? That is Tw minus T infinity. T infinity, this symbol I always give it for the fluid temperatures, surrounding fluid temperature or free stream temperature. It is also later I would name it as the free stream temperature of the fluid. Flowing current is Q, convection. Now this obviously will be the convection thermal resistance. That will be the convection thermal resistance. This is the convection heat transfer rate. Therefore, from the Ohm's law, we can write that from the Ohm's law, the convection thermal resistance is equal to delta T divided by Q. What is delta T here? Tw minus T infinity by Q. So many Kelvin per watt. This is the formula for the convection thermal resistance. Given as 1 upon HA. This is the formula for the convection thermal resistance. Look at that from the Newton's law of cooling. A is the area of convection. I already said in the earlier class also, area of convection is simply the area of contact between the body and the fluid. Wherever the fluid is in contact with the body, we can take it as the convection area. Okay. The area of touch between the body and the fluid, we may brand it as the convection area. If you see, if the higher the value of H, lesser will be the convection resistance. Higher the value of area, lesser will be the convection resistance. This is the fact. This is the fact which we use it in the fins. This is the fact which we use it in the fins. How do the fins increase the heat transfer rate? Later we are going to see very important topic in conduction. How do the fins increase the heat transfer rate? The simple answer is by providing more area of heat transfer. By providing more convection area, fins can more area of contact between the solid body and the fluid. Fins would increase the more area of exposure of the solid surface with the gases or the fluids, and thereby they can enhance, they can increase the heat transfer rate greatly. So that means by providing fins, what are you trying to do? You are trying to do area of convection is being increased, convection resistance you are decreasing, thereby this heat current you are increasing. So higher the value of H, higher the H value, and higher the area of contact, and higher the area of contact. Area of contact between what? Between the solid body and the fluid, and higher the area of contact, lesser will be the convection thermal resistance, implies convection heat transfer rate is higher. That is what we do by providing the fins. So now totally we come across two different thermal resistance. One is for B by Ka and other is that is for the conduction resistance offered by the slab. This is a general convection thermal resistance. 1 upon Ha is a general thermal resistance, convection thermal resistance. Okay.